Anyway, you're wrong.
February is the best month.
Yeah, February's one of the best months.
Why? It's so
hate
depressing.
February. It's
Yeah.
because they like skiing.
No, it wasn't even.
Anything snow related?
Yeah, let's see.
Any snow sports. If you're into snowshoeing or cross country skiing or
Well, skiing's
snow.
not fun when it's like -20.
Also, it's just a short one for you like that. Did you see how I made like the
No,
perfect
it's
square
not.
on the
No, everyone's
rectangle?
Okay, we're gonna talk about 13. Okay, so this is, so you might have been wondering, possibly, like, well, I see how this is working out with money, because when it's money, it's human beings. Human beings make decisions of, oh, this is gonna be interest rate, and this is how often we're gonna compound it. But what happens when it's just a bunch of, say it's nature, okay? A bunch of bacteria, a bunch of little, whatever bacteria are, a bunch of little beetles or something, whatever they are.
Really small people.
Little tiny beetles.
That's how I picture bacteria in my brain.
Yeah. So here's the bacteria. They live in here, this little petri dish.
Yeah, draw the beetle.
So yeah. Boop, boop, beep, boop, beep, boop. Okay, so we know that they triple every 5 hours. Okay? Did I write that right? Yes, they triple every 5 hours. Okay, so how would they maybe know that? Well, I don't know the details of how they measure, like how many bacteria. It might be by mass, but it wouldn't be that complicated to go, oh, there's this much, whatever, there's 100 grams of bacteria. We check 5 hours later, now there's 300 grams. You get the idea? So you have this benchmark of that growth. And then we're going to assume for all these problems, for the sake of simplicity and stuff, that, like, for example, if there was 1 gram, right, and it tripled, and it would triple again, 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 we're going to assume there's no like limiting factor. In real life, there'd be things like how many resources are there, how big is their environment, that would actually maybe that would kind of dampen the exponential growth. But we're just going to assume they have unlimited exponential growth, okay? Does that make sense?
Mm-hmm.
Okay.
Super bacteria.
Yeah. There's some interesting, back to the sci-fi thing, John von Neumann posited a little self-replicating robot that if it could consume elements from its environment to create more copies of itself, could theoretically just consume all matter on the Earth.
Isn't that what Michael Crichton's Prey is about?
Maybe. Von Neumann is from a long time ago, so there's a Futurama about it where there's a bunch of little tiny benders and they keep replicating. That's a reference to the von Neumann machine or the von Neumann robots. Okay, anyway, sorry. So if we know this, then we're going to assume it's natural. So we're going to assume that we can use this equation, right? Does that make sense? Because the bacteria are just constantly growing. Their macro behavior would be like just continual growth. So while each individual bacterium might, those divisions are discrete events, the large-scale behavior is just continuous growth. So what you would do is you'd say, okay, well, I'm going to call this 100 bacteria my principal, my starting amount, 100. And what do we know? We know that when time is, how long will it take to get to 300 then? 5 hours. So let me make sure there's no confusion here. Any questions on this setup here? We sure there's no? Because if you can set this up, you're golden. Then you're like, you know how to do these problems now. So now we're going to solve for R. Or at least we can solve the beginning of them. Divide both sides by 100. What do I do here? Switch it to natural log. So natural log of 3 equals R times 5. And then divide both sides by 5. This is where the calculator comes in. Mr. Quackmolator, what's the natural log of 3 divided by 5? Mr. Quackmolator says about 219. You want to be pretty precise here. I think 5 decimal points should be sufficient. Well, you gotta be cautious because this says 21.972%. I mean, 1/1000% might seem like it is a small amount, but if you're looking at really long term behavior, that actually could have a pretty big effect. Did anyone notice something that is kind of a sort of a big diversion from the money ones in terms of like what kind of number is T?
It's usually
It's usually what?
it's a decimal. No, wait, never mind.
T is really small.
It's usually years, but now it's hours. So that can be confusing, right?
Yeah.
So the upshot here is whenever if you're doing a natural process, analyzing a natural process like this, then whatever the time frame they're giving you, like if they're talking about hours, then T is going to be in hours. If they're talking about a time scale of days, then T can be days. So it can be kind of whatever time unit you want. Does that make sense?
Mhm.
So anyway, what do we do from here?
You plug that into the PERT.
Yeah. So our equation is 100 bacteria times E to, now we know what R is. So R is this number. So you can say this like describes basically the property of the bacteria itself. This is that bacteria's species R value. It tells you how fast it grows, basically. Now, does that make this can throw people off because usually there's like a 5. Where we started, there's a 5. Because that allows it to figure out the R. But now that we have the R, this is actually true for any T value, right? Is making sense still?
Mhm.
All right, now let's answer the last question. So this is one of the answers. That's the equation that governs the growth. The second part says, or the last part of it says, how long would it take for the population to reach 1,000? Well, set it equal. To 1,000, right? And let's solve for time. Divide both sides by 100. And then what?
Natural log 10.
Natural log of 10 equals, and divide, and we are going to get
9.475514.
these calculators are nice because you can like go and grab a number. So if you calculated this number earlier, you can just use the arrow keys to go like grab the number. It just saves you some time. So you get 10.47 hours, because the time was in hours. By the way, does that make sense why, I mean, you might have looked at this earlier and been like, well, if that's 5 hours, and that's 5 more hours, it takes 10 hours to grow by a factor of 9. So it stands to reason that would take a little bit more than 10 hours to get to a factor of 10.
Yep.
I want to show you one more thing. This has historically confused a lot of people, but it's worth it.
Confuse me, huh?
It's like that one song, you know?
I don't know.
Worth it.
What?
You're worth it. You're worth it. You know what I'm talking about? That one song?
The L'Oreal song?
Sure.
They say you're worth it?
I think they're thinking of Party in the USA.
No, that's not that one. That's not how that goes. Okay, watch this. What if I did the same problem but using very sneaky kung fu? Okay.
Mhm.
All right. Listen. If you're like highly prone to confusion, maybe just watch this. But what I just showed you is an ironclad method for solving these problems. But this next one is faster and it's very interesting.
Let's get a zone out for a minute.
Well, I feel bad because sometimes I'll like show this, and then people will be like, "Well, I thought I understood it, but now I'm confused." And that's not my goal here, but I feel like I'd be remiss to not show this to you. What are you confused about? Oh, you're already confused?
No, I'm fine.
I'm glad to answer any questions. Okay, so pretend like I'm starting the whole problem over. Watch this. So I don't know any of this stuff. And I don't know any of this. I'm gonna leave the answer though, because I'm gonna show you how to get the same answer. Okay, if I have 100 bacteria and they're being multiplied by a factor of 3 every 5 hours, that's my function. Boom. So I went straight to the function. Does this make sense? Let's see. Would this agree with the growth described? Like when t is 0, do I have 100? Yeah, plug in 0, you get 100. Well, when I plug in 5 for 5 hours, well, 5 divided by 5 is 1.
300.
10 times 3 is 300. Okay, that agrees. And then how about 10? 10 over 5 is 2. 3 squared is 9. Is this making sense?
That makes more sense.
Mm-hmm.
Right. So this is saying I'm still assuming it's exponential growth. I'm just not necessarily jumping straight to PERT. But watch, this is actually equivalent to the other one. So let's say I set this equal to 1,000, because hopefully right now you're kind of skeptical, like, well, okay, I get the argument, but how's it going to give us the same answer? You're not involving E at all. Divide by 10. How do I solve that? Log base 3 of 10. Do we feel okay about that?
Yeah.
Okay. By the way, if you're wondering where does the natural log come in, you can think of this as natural log of 10 over natural log of 3. There's your natural log of 10 coming into play. Multiply by 5. Through my amazing powers of mental calculation, let's see, 5 times log base 3 of 10. I bet it's something like 10.4796. Just had to do a whole bunch of arithmetic in my head. We can confirm it though. So if I go 5 times, to calculate that, natural log of 10 over the natural log of 3, just to make sure. And yeah, you get the same answer. So if you're confident in knowing the difference, well, here's the thing, you got to know both methods. I'm going to ask you questions on like your quizzes and stuff that go like this, that basically ask you what's the R value for this bacteria. So you have to know how to calculate that. What was it, 0.2 something?
Yeah.
So what I'm saying is you got to know both. If you're finding yourself confused and you're like, I really can only keep one straight, go with the first one. The first one will take care of everything for you. But this is a really nice method. It's very, very fancy. So last thing, what does half-life mean?
The time a thing takes to decay, the radioactive decay.
It's the time of decay of a radioactive element, right?
Yeah, well, it could be anything. It could be jelly beans. It could be, if you got a bowl of jelly beans. And I mean, people don't really eat jelly beans in an exponential decaying way, but if they did.
I do.
I'm saying you get any quantity. You could be like, yeah, how long does it take to get from this to half? So if you're doing a problem that says, say it tells you, oh, the half-life, let's just set one up. Let's knock one out while we're here. If it said, come on, one of these says half-life, I'm sure, right? I know it does. 21, meme number. It says an isotope has a half-life of 16 days. Are we gonna run out of time? How much time do we have?
5 minutes. Wait, no.
We have 30 seconds.
Really?
Better be like.
Oh no, we have
3 minutes.
oh yeah, plenty of time. If your half-life is 16 days, 21, and you have 500 grams of material, and like Zach said, this is a radioactive material is a really common example of something that has a half-life. You have this much radioactive material, it'll, over a long period of time, it'll decay down to half as much, and then after another amount of time, it'll decay to half as much, which is really interesting because in the first period, it might lose 100 pounds, and then it loses 50 pounds, and then 25 pounds, and then 12.5 pounds. That's because the decaying is actually a random process. What's up?
So will it never fully decay then?
Correct.
Will it always just be half?
Yep. That's why they'll have these things and be like, oh, this rock is super old, and they're using an assumption that, oh, the rock used to have this much carbon-14. And then let's say the half-life is whatever, several thousand years. And they'll go, well, we've measured now it has this tiny little amount, and they extrapolate backwards and say, oh, this is how old it must have been. What's up?
They dated the Earth by going, uranium takes like however many billion years to decay to lead, and they're like, well, we have lead, so it's gotta be at least that old.
That's one of the, yeah, there's many other things they use.
Nope.
Yeah.
Only one.
Like carbon-14 is just one of many isotopes they use to like, but yeah, uranium as well. So anyway, you go 500, let's do it the old way. 500 e to the RT equals y. So that's the function. You assume it has that kind of function, right? Well, but we know that if the half-life is 16 days, I can write this. Big drum roll. What number are we gonna put there if I can put 16 in for t? 250. So by the way, does it matter if we went from 1 million grams to 500,000 grams, or if we went from 8 grams to 4 grams? No, you're always going to end up with this 1/2 here. So what kind of numbers are going to be? Think about that. If you're losing stuff. By the way, feel free to invest in my bank, guys. I offer a negative interest rate. You give me your money, and then you pay me for storing it. Yeah. Ours is going to be negative. Yeah. So you're going to find that when you plunge into your calculator, the natural log of 1/2 is a negative number. So what you're going to find here, when you divide by 16, your R value is going to be roughly negative 0.04332. You guys know the drill, right? You go back and you finish the problem using that R value. Or if you're feeling super lit, you can do this. Like that. 500 times 1/2 for every multiple of 16. That's pretty snazzy.
Yeah.